Okay, at this point we are ready to formulate the Noether theorem. We consider, as always today, we consider infinitesimal transformations in extended phase space. Remember the condition for a transformation to be canonical. This was our condition for canonical. Then we required symmetry. Now the symmetry told us that the first term appearing here, h prime minus h times dt, that must equal the right red box epsilon times the square bracket times dt. So by symmetry, we can say, we can replace this term here by epsilon times dh over dq psi dt plus dh over dp chi dt plus dh over dt phi dt. This is what symmetry tells us. From this we subtract the curly bracket chi dq plus, let me leave out the curly bracket, so we have minus epsilon chi dq minus epsilon p d psi plus epsilon h d phi, and this equals epsilon dg. You see, first of all, that now we can take out all the epsilons. Then we can consider motion along an actual physical trajectory. Now, along a physical trajectory, the partial derivative of the Hamilton function with respect to q is minus p dot, minus the total time derivative of momentum. It's minus p dot. Minus p dot times dt gives minus dp. So this is minus dp times psi. So along a physical trajectory, we can make that replacement. In the same fashion, we can take a look at this partial here. Now the partial derivative of the Hamilton function with respect to momentum, that's q dot times dt gives dq. So we have dq. The partial derivative of the Hamilton function with respect to time equals the total derivative of the Hamilton function with respect to time times dt gives dh. So this gives dh. So this is added times chi plus this times phi. Then we have minus chi dq minus p d psi plus h d phi equals dg. Right, then there's another cancellation. We have the second term is dq chi, and then later on that line we have minus chi dq. So these two terms, this one and that one, they cancel. Then what's left? We have a term in there, there's a term dh times phi, and then later we have plus hd phi. This is taken together, this is the differential of h times phi. So we have here a differential of h times phi. What else do we have? We have a minus dp times psi, and later we have a minus p d psi. Taken together, this is the differential minus the differential of p times psi. So we have minus p times psi. And then on the right-hand side we have a dg. We can take that to the left-hand side and can write minus dg. So take this all into the square bracket, and then on the right-hand side we have 0. And this holds along a physical trajectory. So in other words, along a physical trajectory, what's inside the square bracket does not change. Therefore, what's inside the square bracket is a constant of the motion. So here we have shown, we started out from an infinitesimal transformation in extended phase space. We said this is canonical, and it's a symmetry in the sense that physical trajectories are mapped to physical trajectories with the same Hamilton function. And this requirement led to a constant of the motion. And this shows the general result that whenever there's a symmetry, this implies a conservation law. Whenever there's a symmetry, you can derive an associated quantity that is a constant of the motion. And this is the essence of Noether's theorem, that it's the relationship between symmetry and conservation law. And it also tells you how, given the symmetry, how you can determine the constant of the motion. It's the formula above. It's the expression inside the square bracket. Now, all the calculations here I did in one dimension, so I didn't have to carry any indices for my coordinates. Just as for completeness, when you have more than one dimension, or well, generally you have more than 1 degree of freedom, so a number of degrees of freedom is larger than 1, then in this formula for the constant of the motion, you must replace p times psi, you must replace that by the sum over I, pi psi I. And of course then you have these functions that characterize the shift in extended phase space, the psi's and the chi's, they get indices because for each component of your coordinate you have a different shift. I'd like to show you 3 examples, 3 applications of Noether's theorem. The first symmetry that I would like to consider is a symmetry under spatial translation. Invariance under spatial translation means it doesn't matter if I perform an experiment here or whether I displace all my equipment by 2 meters and then I perform the experiment there. I will observe the same dynamics governed by the same Hamilton function. Which functions mathematically generate such a spatial translation? Remember we had these 3 functions, phi, psi, and chi. Phi described the shift in time, in our time coordinate. Well, we don't have any such shift here, so phi is equal to 0. Psi described the shift in the configuration space, so and that's what we have. We shift in space, and the associated function is simply psi equal to 1. So any coordinate q is shifted by epsilon. Q becomes q plus epsilon times psi. When psi is equal to 1, then we simply shift every point in space by a constant epsilon. Psi is equal to 1. And chi is equal to 0 because we don't have any shift in momentum when we do that. We should first check whether such a transformation is indeed canonical. Yes, it is, because this is simply a transformation in configuration space, a time-independent coordinate transformation in configuration space, and you showed on one of the problem sets that quite generally any such transformation is canonical. So yes, it is canonical. Under such a canonical transformation, since it's time independent, the Hamilton function does not change, so h prime is equal to h. And the function g that appears, or whose differential appears in this condition for a canonical transformation, that is equal to 0. Now, what is then, as a consequence of this symmetry, this invariance, what would be the conserved quantity? The formula for the conserved quantity, remember, is h times phi minus p times psi minus g. This is the physical quantity that is conserved when you have this invariance. Phi is equal to 0, psi is equal to 1, g is equal to 0. So what remains is minus p, minus the momentum is conserved, or then also the momentum itself is conserved. So the conserved quantity is p, which is the momentum. So whenever you have invariance under spatial translation, then as a consequence, you have momentum conservation. Or vice versa, momentum conservation is an indication that you have invariance under spatial translation. Consider next invariance under rotation in space. What does a rotation do in Cartesian coordinates? A rotation transforms, and let me say that I rotate around the z-axis. So the z coordinate remains unchanged, but the x and y coordinates are transformed. And they are transformed via a rotation matrix which has the entries cosine epsilon, sine epsilon, minus sine epsilon, and cosine epsilon, where epsilon is an infinitesimal angle applied to the original x and y. When we rotate in this fashion, we rotate position coordinates, then we also have a resultant rotation of the momentum components. That's also an exercise that you did in one of the problem sets when you have a transformation in configuration space, then you have a resultant transformation also of the momentum coordinates, and the momentum coordinates x and y, they rotate in the same fashion, so with the same matrix cosine epsilon, sine epsilon, minus sine epsilon, and cosine epsilon applied to px and py. Now, when the angle is infinitesimal, then we can expand in epsilon, around epsilon equal to 0, and then to lowest order in epsilon, to first order in epsilon, cosine of epsilon is equal to 1, because the next term in the Taylor expansion would be of order epsilon squared. So to first order in epsilon, the cosine is equal to 1. Sine epsilon is epsilon, minus sine epsilon is minus epsilon, and cosine is equal to 1. So this is here a rotation around the z-axis. What are the functions that describe this infinitesimal transformation? Again, we have no shift in time, so phi is equal to 0. We do have shifts in space of our position coordinates. How is the x coordinate shifted? X is shifted to x plus epsilon y. So the psi the function psi x that characterizes the infinitesimal shift of the x coordinate is equal to y. The y coordinate, y is transformed to y minus epsilon x. So the function psi associated with coordinate y is minus x. The momentum is shifted, the px component is shifted to px plus epsilon py. So in the same logic, the function chi that describes the shift of the x component of momentum equals py, and chi y, the shift in the y component of momentum, equals minus px. So these are the functions that describe the infinitesimal transformation in extended phase space that's associated with a rotation around the z-axis in space. Is it canonical? Yes, it is, because again, it's a transformation in configuration space with the resultant transformation also of the momenta, and we know generally that such transformations are canonical. Transformation is time independent, therefore the Hamilton function does not change. H prime is equal to h, and you can verify that also g is equal to 0. This is simply because it's a time independent transformation in configuration space. What is then, when we have the symmetry, what is the associated conserved quantity? Again, we have to look at this expression h times phi minus p psi minus g. Phi is equal to 0, so the first term doesn't contribute. Then we have minus p psi. Here we have several components, so we have to add up the components. So we have minus px psi x minus py psi y, and g is equal to 0. So what is that? Psi x is equal to y, and psi y is equal to minus x. Let me start with the second term, the minus py psi y. With psi y equal to minus x, we have then plus x py, and then the other term, minus px psi x is equal to y, so we have minus y px. And you recognize xpy minus ypx, that's the z component of angular momentum. So we learn that whenever we have rotational symmetry around the z-axis, then the z component of angular momentum is conserved. You can do the same argument for all the other axes. Now, if you have complete rotational invariance, if you have isotropy, so you can do arbitrary rotations around all the axes, then all the components of angular momentum are conserved, and therefore the angular momentum vector is conserved. So rotational symmetry is associated with angular momentum conservation. And then let me consider as a final example shifts in time. So we have time translation, meaning that it doesn't matter whether I perform an experiment now or I perform the experiment in an hour. I will observe the same dynamics governed by the same Hamilton function. It doesn't matter. It's symmetric under shifts in time. Which functions generate such a shift in extended phase space? Well, in that case, the phi is equal to 1, because time is shifted at any point in extended phase space. The time coordinate is shifted by a constant epsilon. But there is no shift in space and there's no shift of momentum, so psi is equal to 0 and chi is also equal to 0. Again, you verify that this is canonical in the more general sense that we discussed yesterday. It's canonical. Again, the Hamilton function is the same. H prime is equal to h and g is equal to 0. Well, what is then the conserved quantity? Then h times phi is equal to h. The other terms are 0. So the conserved quantity is the Hamilton function h. In those cases in which the Hamilton function is equal to the physical energy, this corresponds to energy conservation. So this, of course, provided the Hamilton function is equal to the energy, the conditions that we had discussed earlier. Then invariance under time translation is associated with energy conservation. So one last issue regarding the relationship between symmetry and conservation law. You may have, what we have considered so far are, first we considered symmetries, and then we wondered what is the conservation law that follows from a given symmetry. You may also pose the reverse question. You may have a conservation law. You may find that a certain quantity is conserved, and you wonder what is the underlying symmetry that gives rise to this conservation law. So you want to go the other direction. So you wonder, given some conserved quantity f, what is then the underlying symmetry? And one way you can uncover the underlying symmetry is by considering certain Poisson brackets. Consider first the Poisson bracket of this conserved quantity f with q, the configuration coordinate. Well, the conserved quantity, given that it comes from some symmetry that we still want to discover, must have the form Hamilton function times phi minus p psi minus g, and you take the Poisson bracket of that with q. Let's consider these terms one by one. Let me start with the Poisson bracket of minus p psi with q. There's a product rule for the Poisson bracket. That is minus the Poisson bracket of p with q times psi minus p times the Poisson bracket of psi with q. So, but the Poisson bracket of p with q, that's one of the fundamental Poisson brackets, that's minus 1. The fundamental Poisson bracket says Poisson bracket of q and p is 1. Poisson bracket is anti-symmetric, so Poisson bracket of p with q is minus 1. So we have minus Poisson bracket pq, which is minus 1, so plus, and then psi. We are left with psi. Then we have minus p times the Poisson bracket of psi with q. The Poisson bracket of psi with q, when you use the definition of the Poisson bracket, this is equal to minus the partial derivative of psi with respect to p. So we have minus p times minus partial of psi with respect to p. Together, this gives plus p times the partial of psi with respect to p. Then let me consider next the Poisson bracket of Hamilton function times phi with q. Again, I can split this in two terms by the product rule. This is first of all the Poisson bracket of the Hamilton function with q times phi minus the Hamilton function times the Poisson bracket of phi with q. It's plus the Hamilton function times the Poisson bracket of phi with q. But the Poisson bracket of phi with q, you take the definition of the Poisson bracket, that's minus the partial derivative of phi with respect to p. So we have the partial of phi with respect to p. And then we are left with minus the Poisson bracket of g with q. The Poisson bracket of g with q, again in the same logic, that's minus the partial of g with respect to p. Of minus minus, which is plus the partial of g with respect to p. I claim that the last three terms add up to 0 by the condition that the transformation is canonical. The way to see that is to go back to the infinitesimal canonical transformations and to consider the condition that the transformation is canonical. That's the equation below that features this, this curly bracket. And then you might remember that earlier we had said we can expand the deep psi and the d phi in as linear combinations of dq, dp, and dt. By comparing the coefficients in front of the dq's, we had already obtained an equation for chi. We can also compare the coefficients in front of the dp's. When we compare the coefficients in front of the dp's, then we find that minus p times the partial deep psi over dp plus h times the partial d phi over dp, that this must equal the partial of g with respect to p. So comparing the coefficients in front of the dp's gives a condition that makes the last three terms here add up exactly to 0. So the way, just as a reminder, the way you prove that is that you compare the coefficients in front of the dp. Now, if the last three terms add up to 0, then you see if you have the Poisson bracket of f with q, and you can bring it in this form, some function plus the Poisson bracket of Hamilton function with q times some other function, then you can read off from this result the functions psi and phi. Consider next the Poisson bracket of f with p with the momentum. Again, f must have the form Hamilton function phi minus p psi minus g Poisson bracket with p. Let's start with the Poisson bracket of minus p psi with p. Poisson bracket of p with p is 0, so we just have minus p times the Poisson bracket of psi with p. The Poisson bracket of psi with p is the partial of psi with respect to q. Then we have the Poisson bracket of Hamilton function times phi with p. That's Hamilton function times the Poisson bracket of phi with p, but that is the partial of phi with respect to q, plus the Poisson bracket of the Hamilton function with p times phi. And finally, we have minus the Poisson bracket of g with p, and that is minus the partial of g with respect to q. Now, in this case, the first three terms, again, by the condition that the transformation is canonical, they add up to chi. This is the equation that we had on this earlier page that we also derived from the condition that the transformation is canonical. We had derived the formula for chi. That's exactly the formula that we derived. So you have the form here that the Poisson bracket of f with p equals chi plus Poisson bracket Hamilton function with p times phi. So again, you can read off the functions chi and phi. So this is a possibility to uncover the functions that generate the underlying symmetry if you take the conserved quantity and you calculate the Poisson brackets with Q and P.